Okay. So last class we've been discussing a bit more about the normal random variable, and we got more in tuned with the standard normal random variable, which is simply the same curve we've been seeing a lot these days, but now particularly we have the mean of 0, and then this is spaced out by the standard deviation, which is just 1. So the mean is 0, the standard deviation is 1, and this constitutes as a standard normal random variable. And we do this for many reasons. We study the standard normal random variable for many reasons. One of them is that we can standardize, quote unquote, most of our normal random variables. So if we have, so let x be normally distributed with parameters mu and standard deviation, then our normal random variable can be standardized by subtracting by the mean and dividing by the standard deviation. And then we learned how to, using the table and using the calculator, we learned to find the area to the left. So for example, this would be the CDF function evaluated at 2. So this is the area to the left. It's the area under the curve to the left of 2. And then we also discussed how to find the area to the right of a particular number. We also discussed how to find the area in between and so on. And we used a calculator for that, and we also used the table for that. And then we ended by finding the way to, given the area, so sometimes we're given the area and we have to find what that x value or that z value was associated with. So all of these things we discussed last time about the standard normal random variable. And I want to touch upon one more thing with regards to the normal random variable, but before then, I think we have to discuss something called the variance. I don't think we have discussed it yet. The variance of binomials. So we're going to talk about the binomial again. Because the normal distribution is actually a pretty darn good approximation, similar to the Poisson distribution being a good approximation to the binomial random variable. But to talk about this, we have to just talk about the variance a bit. And to talk about the variance, we have to think about the binomial random variable as a sum of Bernoulli trials. So you guys, I'm pretty sure you guys remember Bernoulli, right? Bernoulli was the first type of, it was the first kind of distribution that we discussed, particularly a discrete distribution. And so we're gonna let x be a binomial random variable. okay? And what that means is that X, so it has a binomial random variable with the parameters N and P, right? So for every binomial random variable, the parameters are N and P. And remember, N represented, for a binomial random variable, N represented the number of independent, or the number of trials, which are independent, the number of trials, and P represented the probability for the success. So right before talking about binomial random variables, we discussed Bernoulli random variables. And Bernoulli random variables, if you recall, what a Bernoulli random variable was. I'm gonna call this X sub I, okay? X sub I, this was a 1 or a 0 if the ith trial was a success. Whatever that means, right? Success. And it will be a 0 otherwise if it were a failure. Now, if we add up the Bernoulli random variables, if we have n of them, if we have more than one Bernoulli random variable, we have what's called the binomial random variable. So binomial random variables are sums of Bernoulli random variables. We kind of hinted at that last time when we first discussed this, but now we're going to use this a bit more explicitly. So a binomial random variable is a sum of Bernoulli random variables. Now, this is a very powerful idea when you're able to break down a random variable that may sound complex to simpler, smaller random variables. This idea is actually, it's very nice, and you'll see, hopefully, why, particularly in this case. So why am I doing this? Because I want to eventually, my goal here is to find the variance of X. I want to find the variance, because I don't think we discussed the variance for binomial random variables as of yet. We know what the expected value, right? So recall one more thing too. The expected random variable, the expected value of the binomial random variable is NP. Well, let me show that. I remember I showed this to you guys and it was very complicated. Remember that? It was like a complicated derivation as to why the expected value was NP. We had to do like a whole bunch of summation manipulations. But if we do it this way, it becomes very simple actually. If you want to find the expected value of the random variable, just take the expected value of the sum. But what we know about expected value is that we can find the expected value of each individually and then add them. But each of these, X sub I, X1, X2, they're Bernoulli. And if you remember, the expected value of Bernoulli was simply P, the probability of a success. And how many P's do we have? We have N of them. So each of these are P's, P plus, all the way to P, but there's N of them, so NP. So you see how nicely, I don't know if you guys recall, when we derived it, it was quite complicated, but now here it's very simple. I'm just adding the expected values of each Bernoulli random variable and adding them together. That's very nice because I don't have to worry about any manipulation of indices for summations. And then now, similarly, if I want to find the variance of x, I'm not going to do the whole summation of, because we know what this is, right? We know this is the expected value of what? Of x squared minus the expected value of x and that whole thing squared. So if we treat the random variable x, which is a binomial by itself, we're gonna have to do the summation of this, and then the probability that gets a little more complex with the summations. So instead, what I'm going to do is I'm going to find the variance of the sum of Bernoulli random variables. And one thing that is embedded in this is the idea of independence. X of 1, X of 2, X of n, they're independent events or random variables. They're independent. They don't affect one another. That's what happens when you have a binomial random variable. They're independent, right? Since they're independent, and one of your homework problems that you discussed that we did in the previous, not the one that we just had, but the one before that, there was a problem that you had a sum of random variables for the variance. And what happened was that because they're independent, you can add the variances individually. So you can find the variance of x sub 1 and then add it to the variance of x sub 2 all the way to the variance of x sub n. And now look at the variance of just one of them. So x sub I. What would be the variance of x sub I? So, Alexandra, so the expected value operator, the operator that takes a random variable and finds the expected value of that random variable is linear and will always be. The issue is that the variance is not always linear. And that has to deal with the fact that some random variables, yeah. So that's what I'm saying. We don't really care about whether it's independent or not for expected value. We can just separately find expected value of the sum of random variables. However, when we talk about the variance of a sum of random variables, we can't just simply do this. We can't. We cannot. It's a bit more complicated to talk about a sum of random variables and its variance. However, because these are independent, and only if they're independent random variables, then you can have this linear property hold for variance. So this only holds if this idea only holds, this linear property only holds if the sum of random variables, not if the sum, is if the random variables themselves are independent from one another. And I was just referencing one of the homework problems that you guys had done, something similar to this when you had a sum of random variables. And what occurred was that the variance of that sum of independent random variables were just the sum of its variances because they were independent. And I showed during office hour twice why that was the case. But now because they're independent and the sum of the variance of the sum of independent random variables equals the sum of the variances, we look at one of them. So what's the variance of just one of the Bernoulli random variables? Well, we're going to use the idea again of the definition of the variance, right? We take the expected value of the random variable squared minus the expected value of the random variable, and that thing is squared. So that quantity is squared. Well, we already know that the expected value of one of them, right? The expected value of one of these guys is P. So this here will be P, but I'm squaring it. So this will be minus P squared. Now, what about this? What about expected the random variable being a Bernoulli, but I'm squaring it? So go back to what a Bernoulli is. If I square this, that means I'm squaring all of the values of x. But by squaring 0 and by squaring 1, I still get the same thing. So squaring the random variable results in itself. So this is the same as the expected value of just simply x sub I. They're the same. They're equal. They're the same. But what's the expected value of one Bernoulli random variable? It's P. So the variance of a Bernoulli random variable is P minus P squared. Or people sometimes write it as P multiplied by 1 minus P. And then you start to see, oh, this is the multiplication of the probability of success multiplied by the probability of failure. That's the variance. But this is only for one of them. I have n of them. So I have P times 1 minus P plus P times 1 minus P plus P times 1 minus P. So I have n of them. So the variance of x, the Bernoulli, a binomial random variable, would be n times P times 1 minus P. So this is the variance of a binomial random variable. This here is the variance of a Bernoulli random variable. Okay, so why did I kind of go back to discrete random variables if we're with continuous, particularly the normal distribution? Why go back? Well, now we're going to see that we can actually approximate. So we can use the normal distribution to approximate binomial distributions. So that's the idea. So now that we know the variance of a binomial, we also know the standard deviation. Remember, standard deviation is the square root of a variance. So that's what we're going to be doing. We're going to be standardizing, quote unquote. We're going to morph. I don't know what's the best word for that, but we're going to standardize the binomial distributions using the normal distribution. So what do I mean by that? And so the normal distribution is used particularly when n is large. So if you recall what binomial distributions look like, right? If you were to look at the probability mass function, so let x be a binomial random variable. with parameters n and p, and we're gonna make p large. I mean, not p, n. Make n large. So the idea is that we get some kind of probability mass function that is very symmetric. Recall that this is the way the probability mass function is, right? Remember, this is n choose x, p to the x, 1 minus p to the x. The probability is maximized when it's in the middle, when you have x being in between. It's the middle number of the n trials, because this is when this product is at its maximum. Now, as n gets much larger, as n gets bigger and bigger, right? These probability like bars become closer and closer, and they look very much like what? They start to become very much like the normal distribution. So that's why when n is really large, we use the normal distribution to approximate the probability. Now, why is that useful? Well, let's look at an example. Okay. For example, let x be the number of times that a fair coin is flipped. And let's make n 40 times. Yeah, that is. So let x be the number of times that a fair coin that is flipped 40 times lands on heads. So we've done things like this, right? So x is a binomial random variable because you're flipping a coin and it has two outcomes. And we're doing this 40 times. So this here will be my n. And because it's a fair coin, p is a half, okay? And then, so then I'm gonna ask, what is find the probability that that there are at least let's say 10 heads. At least. So what does that mean? I want to find a probability that there are at least 10 heads. So x is greater than 10. Now, kind of go back to the world of discrete distributions. So if you're at least or equal to 10, what does that mean? How would you find this probability? You can do that. Yeah, you can do that. That makes sense. 1 minus the probability. I would do that, yeah. X less than 10, which would be what? 1 minus the probability that x is less than or equal to 9, right? Because this is a discrete world, right? So if you're less than 10, then you're going to be 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. But even when you did this complementary counting, a complementary probability step, What's the issue? Do you see the issue here? I have to find the probability when x equals 0, plus the probability when x equals 1, plus the probability when x equals 2, all the way to the probability that x equals 9. The problem is it becomes inconvenient. It becomes computationally annoying, for lack of a better word, right? We're going to have to compute the probability for each instance, add those up, subtract it by 1. And this is if n is 40. What if n was 100? And so these things start to become problematic in terms of computing. And it's really just an annoying part of it, right? Because then it's finding the probabilities is straightforward. It's just that you have to do it many more times than you probably would like. So the idea is, you know what? I don't want to be doing this every single time. I want to find a way. Is there a better way? And actually, there is. And that's if you approximate it using the normal distribution. Because, like we just saw with this little diagram, the larger n becomes, the more the probability mass function takes the form of the normal distribution. So then what we're going to do is we're going to approximate. So this is the exact, right? This would be the exact probability up here. If we compute this, this would be exact probability of what we're asking, right? But now we're going to use the normal distribution. So instead, we're going to use, to approximate the above probability, we will use the normal distribution. Now, how do we do that? Well, it's very similar. It's going to be, we're going to normalize it. So z now will be like, so that's why I put these approximate symbol, not the equal. So z is the normal distribution, okay? This is the standard normal. This standard normal is similar to the random variable binomial subtracted from the mean divided by the standard deviation. The issue is that the reason why we put this approximate symbol, I put it in here, is because x is binomial. It's a binomial random variable. We can't just say, oh, a discrete distribution is the same as a continuous distribution. We can't do that. But it's approximately. Now, what does this mean and what is this sigma? Well, the mean is the mean of the binomial distribution, which is what? NP. And the standard deviation is the square root of the variance. But we discussed what the variance was. Do you guys see that? So that's what we're going to do. We're going to find the expected value. What's the expected value? We should know that. We should be able to compute that. N is what? N is 40. 40 times a half, which is 20. So x minus 20, right? And then we're going to divide that by the square root of, well, what is 40 times a half times 1 minus p is also a half. So it's 40 times a half times a half. 40 times a half is 10. So when we take our binomial random variable, subtract it by 20, divided by the square root of 10, this new random variable that we created is similar to approximately the standard normal distribution. Because remember, we did the same step here to create a normal distribution x and make that into the standard normal. That's what we would do. We're doing the same process, but now we're doing this upon a binomial random variable. So the mean and standard deviation is given by the mean and variance information that we know of binomial random variables. So now let's go back to what we wanted. So the probability, we want x to be greater than or equal to 10, which is the same thing as saying 1 minus the probability that x is less than 10, right? Less than 10. Okay. Let me just see. So if it's less than 10, so what we're going to do, so from here, there will be a little approximation from here, right? So from here, this is exact, but the moment I do this, this will be approximate. This is going to be the probability that x, so what we're going to do here is we're going to say this is less than 9.5. Okay, so this little step here is called continuity correction. The reason why we do this is because we're going from discrete to continuous, right? So if this was like, this was the 10, right? And we want everything to the left of it. We want 9, 8, 7, so on, 6, right? Then we're gonna just, instead of calling it this 10, we're gonna find the probability from 9.5, which excludes 10, but includes everything else. So we're gonna be just by 0.5, we're gonna either add or subtract by 0.5. This is what the continuity correction does. So we're gonna either add or subtract our original number in the binomial world into the continuous world. We're gonna subtract or add by 0.5. This is just a common step called the continuity correction step. Okay. And then from here, we're going to do exactly what we said. X minus mu over standard deviation, which is less than or equal to 9.5 minus 20 over square root of 10. So this is 1 minus probability. So we went from, so the idea is that we went from binomial to normal. That's the idea. We went to normal. So this is the probability that's less than. Now I have to use some more calculator business here. We have 9.5 minus 20. We're dividing this by the square root of 10. So this is negative 3.32. And so from here, we can use the table, or we can just use our calculators to find so this becomes 1 minus the distribution, the cumulative distribution function evaluated at negative 3.32. So then when we do that, what does this become? So let me show you using my calculator here. Share this. So we're going to go to second vars. We're going to use the normal CDF. This will be negative infinity to negative 3.32. And then our mean will be 0 and our standard deviation will be 1 because we just standardized it. We get a really small number. So this becomes 1 minus the answer. And we get 0.99. So we get a really, really large probability. We get 0.9999549, dot, 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 dot. So that's the probability, according to this approximation, that's the probability that we will have at least 10 heads. Approximately. Now let me see if we can actually find the exact, using the exact probability, using binomial. So we can actually find the probability of the CDF. So the CDF, let me see, this was probability. So 1 minus, right? Until 9. So the number of trials was what, 40? The probability here was 0.5. And the X value that I'm going to go up until is 9. So if I press that, and I do 1 minus that, I get 0.9966. So the number that you just see right now, this one is the exact binomial probability. So that's if we actually just would never have approximated it using the normal distribution. It's 0.9966, blah, 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 right? But the normal distribution is quite pretty good. It's a pretty good approximation. For the first 3 decimal points is the same. So that's the idea. We can use the normal distribution to approximate binomial distributions. Any questions about that? Does everybody see why it's useful to use a normal distribution to approximate? Or does anybody see how we do this? Any questions about how we do this, the continuity step? Does everybody understand what I mean by that? Yes, it makes sense. Okay. Thank you. Okay, so let's do one more example just to like make sure. Let's see. Hold on one second. Okay, something like this. So each item produced by a certain manufacturer is independently of acceptable quality with probability 0.95. So our success of being acceptable quality is 0.95. So this will be our P, and this will be considered success, right? And then approximate that at most, let's say 20 of the next 150 items produced are unacceptable. So for a fact, this 150 here will be our n. So do you see that this is going to be a binomial random variable? So what is x? So let x be the number of acceptable quality items. So if I want to know what's the probability, or what's the approximate probability, did I miss? Yeah, pardon me, I missed the statement. Approximate the probability. Approximate the probability that at most 20 of the next 150 items produced are unacceptable. So if at most 20 are unacceptable, how do I revert that to being acceptable? How do I reformulate this or rephrase this statement here? At most 20 of them will be unacceptable. So then, Mir, what do we say? If it's at most 20, then what? 1 through 80. So I'm talking about like how do we represent, how do we say this using the, instead of using unacceptable, the phrase acceptable? So if it's at most 20, being at most means it could be 20, it could be 19, 18, all the way to 9 to 0, right? We can have at most 20, 0 is included, 1 is included, 2 is included, all the way to 20. So that means that I'm getting a lot of different answers here. If you're at most 20 being unacceptable, then that means that at least, right? At least what? At least 130 are what?
Accept.
Yeah, at least 130 are acceptable. So that's equivalent, correct? That's an equivalent statement. If you're at most 20 of the next 150 are unacceptable, then at least 130 are acceptable. So then what I'm trying to find is the probability that what? X is bigger than 130. Right? That's what I'm looking for. X is bigger than or equal to, pardon me, 130, correct? So again, we can find this probability exactly. So this is the exact one. And how would I do that? I can do the 1 minus thing, but I wouldn't want to do the 1 minus thing because if you think about it, if I do 1 minus the probability that X is less than 130, then I'm gonna have to find a probability of 1, 2, 3, 4, 5, all the way to 130. That's the idea. But with the calculator now, that idea is actually no problem. So this is X less than 130, right? But uh, with this continuity correction thing, what is this gonna actually be? Approximated to be. So it's gonna be one of the probabilities is gonna be what? X is gonna be less than. Remember when we do that little continuity correction step? We either subtract or add by 0.5. Yeah. So because we want to find numbers less than 130, we don't want to include 130. So we're going to subtract by 0.5. So this will be 129.5. Okay. And now we want to find what is the expected value. What is the expected value, which is NP, right? So this is 150 multiplied by 0.95. So what's 150 multiplied by 0.15? 150 multiplied by 0.95 is 142.5. And then what's the variance? What's NP1 minus P? So it's 150 times 0.95 times 0.05. So it's 150 times 0.95 times 0.05. And I get 7.125. And if you take the variance, the square root of that, that would be your standard deviation. So the square root of 7.125 is 2.669. So I'm just going to write it as 2.669. Okay? Dot, dot, dot. So I'm going to use that now to approximate. So this will be the probability that x minus mu over standard deviation is less than 129.5 minus 142.5 all over 2.669. So this now is the probability that my z is less than, and then more numbers here. So this is 129.5 minus 142.5. So that's negative 13. 13 divided by 2.669. Yeah, this is going to be negative 4.870. Okay. And then from here, this is the standard, this is the cumulative distribution of the cumulative distribution function for the standard normal random variable. So now this is standard normal. And then we can use our calculator for that. And we can go to second vars normal distribution here. It's negative all the way to negative 4.87. This will be a tiny number. Then you do 1 minus that, and that will produce a really large probability. So it's going to be 0.999. So usually this is not not the case. 0.999. There's a lot of nines. So the idea is that the probability that at most 20 of them will be unacceptable is a pretty high number, because at least 130 are acceptable. Okay. And let me just do one more example. What if I want to find, using the same example here, what if I want to find the probability that what if I want to find the probability that x equals 30, for example? So this is the probability that exactly 30 are acceptable. So I can do this just straight up way, right? By doing 150 choose 30 of 0.95 0.95 to the 30th power multiplied by 0.05 to the 1/20th power. Actually, this number will be kind of small. I wanna show you a better example. So let me see, 150. So let's say this was 80 instead, pardon me, instead of 80, let's do 80. So what if 80 of the items are acceptable? So this will be 80, this will be 80, and this will be 70. Okay, and then you can put this in your calculator. So if we put this in our calculator, we're going to use the binomial distribution. And it's PDF because we want just one, right? So the trials are 150. The probability here is 0.95. And the X value here is 30. Okay, so we get 0 because it's a pretty, I guess that's not, it's too big. That's the problem. It's too big. Let me see. And it's too large. Oh, I put 30. Pardon me. I should have put, I'm putting 80. Why did I put 30? It's still small. That's the thing. The probability is still pretty small. But anyways, this number here is this number here is 9.32 times 10 to the negative 50. That's the probability, which is pretty tiny. I still want to show you guys how I can use the correct continuity correction with along with the normal distribution. So how we're going to do that is we're going to, instead of finding a particular value, right, for 80, we're going to add and subtract by 0.5 because I want to include this continuity correction step here. So this 80 here is, I'm going to change it. I'm going to change this to 80.5 and 79.5. Okay. And so then I'm going to do the same exact thing. The probability, right? 79.5 minus, what is it? Minus 142.5 over 2.669 is less than the standard variable being between 80.5 minus 142.5 divided by 2.669. So I hope you guys understand why we add and subtract this 0.5 is because if we were to approximate it using continuous random variables such as the normal distribution, I cannot find the value of I cannot find the probability of the value of one single number. Remember, when we find the probability, for example, if x equals 80, if x was a continuous random variable, this would be equal to the integral from 80 to 80 of your PDF, but we know this equals 0. So this will always equal 0 if you write it this way in the world of continuous random variables. That's why we have to add and subtract this 0.5 because it becomes like that slither. It becomes a slither here underneath the normal random curve, right? So this 80 here that we have, I'm kind of just, if this was 80, I'm just making sure that I'm finding the area of that strip. So I'm doing that by adding 0.5 and subtracting by 0.5. I hope that makes sense. And then, again, this is just an approximation. This here is approximately. So let's see if we get the same number that we get here. Let's see if we get something similar. So this is the probability, and then we use more computation here. So this will be 79.5 minus 142.5 divided by 2.669. So this is negative 23.6, and that is between 80.5 minus 142.5 divided by 2.669. So this is negative 23.229. Okay, and then we're going to find the probability that my normal, standard normal random variable, again, this is standard normal, is between these two values. And it's going to be a really tiny probability. It will be. So we go back. So the second vars, and I'm going to use CDF. So the lower bound will be negative 23.6. And the other one will be negative 23.229. Stays the same. And we get something really tiny, 0. So yeah, this is really not like really small probability, which is, it's too small for even the calculator to do. So 9.32 times 10 to the negative 1/50th power is basically, for your calculator, a 0, essentially 0. So I guess the numbers here are too big. The n is too big, and maybe not the greatest example here to show, but the idea is that the normal distribution approximates the binomial distribution. Okay. Yeah, it was good to see. Yeah, the idea is that you can approximate the probability of a specific value for a binomial random variable. I can do so by transforming it into a problem in the world of continuous random variables, particularly with the normal distribution. Okay, so essentially these are the same, essentially, but yeah, your calculator just says it's 0. That's how how much of a slither it is on the continuous PDF distribution. Okay, so we've discussed how we can approximate the binomial distribution utilizing the normal distribution. And we'll come back to the normal distribution, particularly when we talk about the central limit theorem, which is probably the cornerstone of probability, of a class in probability. The central limit theorem is the grand gem. But we're going to now talk about one more type of continuous random variable called the exponential. And of course, there's many others, continuous ones, but these are like the main ones. So we talked about uniform random variable. We talked about the normal distribution, normal random variable a lot. Pardon me. And then now we're going to do the exponential. The exponential random variable has this probability density function. It's again with this lambda business. So lambda e to the negative lambda x, and this is if x is greater than or equal to 0, and it's 0 otherwise. Okay, that's the PDF. What's the CDF? Well, f of x, if you recall, this is the probability that x is less than little x, which is the integral from negative infinity to x. And you know what, let me call this, let's call this a, just to distinguish. So this is going to be the integral of f of x dx, which is negative infinity of a of lambda e to the negative lambda x dx, and lambda is a constant, okay? lambda is a constant. So how do we integrate this? Well, we can take the lambda out. We get negative lambda a of e to the negative lambda x dx. So what's the antiderivative of e to the negative lambda x? Does anybody know? Negative e to the, yeah, but I think so if you take out the lambda e to the negative lambda x, I think you guys are forgetting the e, it's e to the negative lambda x divided by negative lambda. And the reason why is because if you take the derivative of this, right, by chain rule, right, this comes out in front and these lambdas cancel. So you're left with this. So the antiderivative, remember you have to divide. And this goes from what? This goes from a to negative infinity. But of course, when we evaluate this, this will be what? This will be e to the negative lambda a over negative lambda minus, we're going to take the limit as x goes to negative infinity of e to the negative lambda x over negative lambda, right? Oh, and there's one thing. So remember the way the PDF is defined? The PDF is f of x, right? This is exactly what the cumulative distribution function is. It's everything up until a, right, from negative infinity. But when x values are bigger than or equal to 0, this is when we have f of x. So f of x only occurs when this lower bound of integration should be 0, not negative infinity. Because at negative infinity, your function is 0. So this bottom function here should be 0. That's something I glossed over. And this is 0. And so this here is not the limit. This is just going to be simply e to the negative lambda times 0 over what? Over negative lambda. So then we have lambda times negative e to the negative lambda a over lambda. And then this here is e to the 0th power, which is 1. This is positive 1 over lambda. And then you can distribute that lambda, and this becomes negative e to the negative lambda a plus 1. Or in other words, 1 minus e to the negative lambda a. And this is for a being greater than or equal to 0. And this is the probability density function for a exponential random variable. So we know the PDF and we know the CDF. Okay, any questions about the integration part? Everything okay with that? So then once we have that, then we have to just calculate a few more things. So what would be the expected value of this new random variable? Well, we have to do the integration, right? Negative infinity to infinity of x times f of x dx. So this becomes what? 0 to positive infinity of x times lambda e to the negative lambda x dx. And then how do I do this? How do I integrate this? So this starts to become more of a Calc 2 classroom for a little bit, a Calc 2 lecture. because we have to integrate. So how would you integrate this? Does anybody have an idea what integration technique we can apply? By parts? Yeah, integration by parts. So what would be how do we arrange this by parts? So what would we use? So integrate by parts, right? Lambda x would be u. Um, Actually, let's put the lambda outside for a moment. So this becomes 0 to infinity of x times e to the negative lambda x dx. So u will definitely be x. U equals x, which would mean that du, or I should say, I like using u prime. U prime equals dx, right? And then what is v prime? V prime would be this guy, would be e to the negative lambda x. But what would be the antiderivative of e to the negative lambda x? Yeah, u prime, you can write this as 1. You're right, as 1. And then what would be the antiderivative of e to the negative lambda x? We talked about that already, right? This is e to the negative lambda x over negative lambda. So then now what does this become? This becomes lambda multiplied by x times e to the negative lambda x over negative lambda from 0 to infinity. This becomes what? Minus what? Minus the integral of what? Minus the integral of, so usually it's this u dv, right? So what is u dv? Isn't it u prime? It's just see, isn't it u prime? Yeah, it's u prime v, right? So this becomes e to the negative lambda x over negative lambda dx from 0 to infinity. So what happens here? When I take the limit as x goes to infinity of x to the e to negative lambda x over negative lambda subtracted by 0. When I plug in 0, this just becomes 0. When I plug in x goes to infinity, what does this become? Doesn't this all become 0? Why does it become 0? Well, we have an exponential function multiplied by linear. So this is going to overpower, right? This is going to overpower whatever happens with this one. You can also try doing this using L'Hopital's rule, but you'll see that this here overpowers this growth as x goes to infinity, and this is negative. So it's exponentially decaying very quickly. So this is going to 0. And then we have to integrate this. So I can take out the negative lambda in the denominator and I get positive 1 over lambda, the integral from 0 to infinity of e to the negative lambda x dx. And so if I distribute the lambda here, this goes away. So I really just have this 0 to negative to the infinity of e to the negative lambda x dx. So this becomes e to the negative lambda x over negative lambda from 0 to infinity. This becomes the limit as x goes to infinity of e to the negative lambda x over negative lambda plus, well, it should be minus e to the negative lambda times 0 over negative lambda. But again, by the same token, x goes to infinity. This is an exponentially decaying function. So this goes to 0. And then this equals what? This here is 1. Negative divided by negative is positive. So it's 1 over lambda. So the expected value of x is 1 over lambda. So this lambda business comes up again. And so we can find the expected value, but I just want to do one problem really quickly utilizing this. So exponential random variables are utilized for distributing the time. It's a distribution of the time that it takes for an event to occur. So for example, suppose the length of a phone call in minutes is exponentially distributed, which just means that the PDF is the PDF of an exponential random variable with parameter lambda being 1 over 10. So it says find the probability. You have to wait. Find the probability that you have to wait for a public phone booth, which we don't really have those anymore, for a public phone booth if someone's ahead of you, if someone is ahead of you for more than 10 minutes. So you're at a phone booth and you're waiting for somebody to get off the phone so you can call, right? And you want to see what's the probability of having to wait 10 minutes for that to happen, for that phone call to occur, which means that I would have to wait. The length of the phone call is exponentially distributed, so I have to wait 10 or more than 10 minutes. So I'm looking for the probability that x, which is the length, right? This is x. So let x be bigger than 10. It's exponentially distributed, right? So I can write this as what? 1 minus the probability that x is less than 10. But then what is this? This is the CDF, right? Don't we know the CDF? The CDF is what? 1 minus e to the negative lambda of 10. So this is equal to 1 minus e to the negative lambda, or 10 lambda, or lambda 10, doesn't matter. Lambda times 10. But then when you do when you distribute that negative, the negative 1 minus 1 goes away and this becomes positive e to the negative lambda times 10. But what is lambda? Lambda was 1/10. So this is really e to the negative 1, or 1 over e. So the probability for you to wait that long is 1 over e. And 1 over e is approximately 0.368. So the application of the exponential random variable is very similar to the other random variables that we've discussed. It just has a different structure now. It has a PDF that looks like this. So once we have this PDF and then we understand the CDF as well, then finding the probabilities of exponentially distributed random variables is actually just applying this new PDF and CDF. Yes, Mir.
Do we have to be